Hello viewers, my name is Dr. Kishen Ajay Kumar, Associate Professor, Department of ECE from Institute of Aeronautical Engineering, Dundigal, Hyderabad. And today we are going to discuss about the topic Introduction to Radio Wave Propagation, which is under the course Antennas, Waves and Propagation. Let us start our session today regarding the radio wave propagation. So there are some international standard frequencies. So whatever the antennas that we have discussed earlier, all these antennas belong to any one of these frequency ranges. Their operating frequency ranges between the radio frequency spectrum ranges, that is very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. So very low frequency, the range comes between 3 kHz and 30 kHz. And a low frequency, the range of low frequency is 30 kHz to 300 kHz. And the medium frequency range is 300 kHz to 3 MHz. And ultra high frequency range is 300 MHz to 3 GHz. So Maxwell's, there are two scientists who discovered about the electromagnetic wave propagation. So earlier in the year 1864, Maxwell, he told that the electromagnetic waves that are propagated, that are radiated from the antenna, they travel with a velocity of light. That means the time varying electric and magnetic fields together gives rise to electromagnetic waves, and those waves travel in the space with the velocity of light. And later, Hertz, the scientist, he told that whatever the electromagnetic waves produced by the antenna, they travel between the transmitting antenna to the receiving antenna in only straight lines. So Maxwell told that whenever an input supply is given to any conductor, that is a time varying AC signal is given to the conductor, then electric and magnetic fields are produced, which gives rise to electromagnetic waves traveling in space with the velocity of light. And Hertz, the scientist, he told that all the electromagnetic waves produced from the antenna, they travel from the transmitting antenna to the receiving antenna in straight lines. And here, the electric and magnetic waves that are produced from the antenna, both are mutually perpendicular to each other. So you can see here, if we can represent the wave in the form of a three-dimensional representation, one is the Z plane, the other one is the Y plane, the other one is the X plane. So you can see here, the direction of propagation here in the figure is, it is in the Z direction. So whatever the waves that are produced, the electric waves are in the direction of X, and the magnetic waves are in the direction of H, you can see here. And these E and H are both perpendicular to each other. And these mutually perpendicular electric and magnetic waves are orthogonal to the direction of propagation of the wave. Mutually perpendicular and orthogonal to the direction of propagation wave. Hence, these waves are, we call it as a TEM waves. We call these waves as the TEM waves, that is transverse electromagnetic waves. Now let us see the basic concept of the radio wave propagation. So whenever we supply some amount of current to the conductor, some amount of electric field and magnetic fields are produced. And moreover, some amount of current or some amount of radiation lies inside the conductor, and some amount of power will be escaped into the free space. The power escaped in the free space is nothing but the radiation. So whenever there is a conductor is there, and if you supply some input signal to the conductor, power is radiated, and some power will be in the form of resistance, and some amount of power will be escaped in the free space. The power that is escaped into the free space, we call it as the radiation. In other words, the power escaped in free space is in the form of electric field lines and magnetic field lines. So the electric field and the magnetic field and the direction of propagation, all these three are orthogonal to each other. That means if the electric field is in the X direction and the magnetic field is in the Y direction, then the wave is going to propagate in the Z direction. So here, the concept of wave propagation starts from a conductor, a basic conductor. So when we give an input signal to the conductor, oscillations takes place. When we supply the input current to the conductor, when we feed the conductor, then the positive charges and the negative charges oscillate each other. They move to and fro at a greater velocity. At a greater velocity, when these move to and fro with a greater velocity, radiation is possible. So that is the radiation is producing from the conductor in the form of power. That is the power escape into the free space is nothing but the radiation. And before going into the modes of propagation, let us see some basic concepts of radio wave propagation. What is a ray and what is a wavefront? A ray, it is a line drawn along the direction of propagation of electromagnetic wave. Basically, a ray indicates relative direction of the wave propagation. Basically, a ray indicates a relative direction of the wave propagation. A wavefront is nothing but a surface of constant phase of a wave. So a ray directly that is transmitting from transmitting antenna to receiving antenna without any striking the obstacles, we call it as a ray. Suppose you can see here A and B, there is only one path, we call it as a ray. And here you can see here C and D, there is only a single line and the direction is towards this D, we call it as a ray. So here the direction of propagation is from C to D. And here the direction of propagation is from A to B. So we call this type of pattern, we call it as a ray. So a ray is a line drawn along the direction of propagation of the electromagnetic wave, which indicates the relative direction of the propagation, wave propagation. A wave is nothing but, you can say the wavefront, it is nothing but a surface of a constant phase of a wave. Such a wavefront can be obtained by joining together all the points of equal phase on the rays propagated from the same source. Suppose let us say, let us take a stone. When we drop a stone inside the water, some waves are produced surrounding the stone. So when we throw a stone into the water, some waves are produced surrounding the stone. So these waves are at equal phase and equidistant from the same source, and these are circular, and the waves produced from the same source are circular. Hence, we call it as a wavefront, or circular wavefront is produced from the when a stone is dropped into the water. So these are known as wavefronts. These are known as wavefronts. The waves produced from the same source. These are at equal phase from the same source. So a wavefront with the surface perpendicular to the direction of propagation is shown in the figure, as shown in the figure. See here, there is a point source here in the diagram. The point source is producing rays in the direction of propagation of the wave, and this is the direction of propagation of the wave, and this is the direction of propagation of the wave. And this direction of propagation of the wave and the rays both are perpendicular to each other. A wave front with a surface perpendicular to the direction of is shown in the figure. So this is the direction, and this direction is perpendicular to the source which is placed with respect to the surface. Let us see the classification of waves. So there are different types of waves in the radio wave propagation. Let us see one by one. That is a plane wave. A wave for which equiphase surface in a plane is known as a plane wave. A plane wave for which a equiphase surface in a plane is known as a plane wave. So I shown the figure. All the phases of all the waves produced are having the same phase. All the waves that are produced in a plane are with equal phase. Hence, the wave is said to be the plane wave. The wave is said to be the plane wave. And what is a uniform plane wave? A wave for which the equiphase surface is also equiamplitude, then it is called a uniform plane wave. So the phase will be equal and the amplitude will be equal. So waves which are having equal phase and equal amplitude, those waves we call it as uniform plane wave. Those waves we call it as the uniform plane wave. It means that you can see here, these are having the phase of these two waves. This is 1 and this is 2. The phase of these two waves is same, and at the same time the amplitude. The amplitude is 5 volts and this amplitude is 5 volts, and these two waves are said to be uniform plane waves. These are said to be uniform plane waves. If the phase of the two waves is same and at the same time both are in equal amplitude and both are having the equal amplitude. We call it as a uniform plane wave. You can see here this is one wave and this is another wave. Here the phase is same and the amplitude is same. We call it as a uniform plane wave. You can see here in the figure a non-uniform plane wave, a wave for which there is no equal phase and there is no equal amplitude surface and both are not parallel to each other, then such a wave is known as a non-uniform plane wave. So plane wave means equal phase and equal amplitude, but a non-uniform plane wave is exactly opposite to the uniform plane wave. There is no equal phase and equal amplitude between the waves, and both are not same and both are not parallel to each other. Then such a wave is known as a non-uniform plane wave. A non-uniform plane wave. And there are other types of waves which is known as a slow wave. A wave in which the phase velocity is always less than the velocity of light is known as the slow wave. Here Vp represents the phase velocity and Vc represents the velocity of light. If Vp is less than the Vc, then such type of wave we call it as a slow wave. So Vp is known as the phase velocity and Vc is known as the velocity of light. Such a wave we call it as a slow wave where phase velocity is less than the velocity of light. And next one is a forward wave. A wave traveling in a required direction is called a forward wave. A wave traveling in a required direction is called as a forward wave. That is in the intended direction. A wave traveling in the intended direction is known as a forward wave. And a backward wave is one when a forward wave strikes the reflecting surface and returns back, then such a reflected wave is called a backward wave. So whenever we are going to transmit a signal from a transmitting antenna, if there is any obstacle, any obstacle here placed between the transmitting and receiving antenna, the signal goes to strikes the surface of the obstacle and it reflects back to the transmitting antenna, or it may be reflected to another directions also. The wave is going to reflect in other directions, or the wave is going to reflect back to from the same source. So such type of waves we call it as a backward waves. And transmitting a wave, traveling wave, a wave propagating in one direction without any reflection is known as a traveling wave. A wave propagating in one direction. This is the transmitting antenna. It travels only in one direction without any reflection. That means this transmitting antenna has only one path or line, or there is a line of sight between the transmitting antenna and receiving antenna, and there is no any obstacles between the transmitting and receiving antenna. The wave directly propagates without any reflection. That those waves we call it as a traveling wave, which travels in only one direction only. There are different designations of radar frequency bands. There are some standard international frequency bands or symbols used for frequency bands. So as we have seen earlier, there are VHF band, UHF band, frequency spectrum is represented as VHF, UHF and SHF. So similarly for radars or for satellite communication, we can also represent, there are some standard frequency bands we represent in terms of gigahertz, like P band, L band, S band, C band, X band, KU band, K band, KA band, Q band, and W band. So these frequencies ranges are fixed. These frequency ranges are fixed and no one can change these frequency ranges. So suppose let us say P band. So the range of P band is from 0.25 to 0.5. And the range of L band, it is from 0.5 to 2 gigahertz. The range of L band is from 0.5 to 2 gigahertz. And the range of S band, is from 2 to 4 gigahertz. The range of C band from 4 to 8 gigahertz. This is C band. The range of X band is from 8 to 12. From 8 to 12 gigahertz. So like this, there are some different frequency ranges fixed by some technical international standard organizations. So these are the letter designations in the frequency bands. L band operating frequency band is 1 to 2 gigahertz. And S band is 2 to 4 gigahertz. And C band is 4 to 8 gigahertz. And X band is 8 to 12 gigahertz. And KU band is 12 to 18 gigahertz. K band is 18 to 27 GHz, and Ka band is 27 to 40 GHz. V band is 40 to 75 GHz, W band is 75 to 110 GHz, and MM band is 110 to 300 GHz. Let us discuss about the modes of propagation. So, what are the different modes of propagation we are having? The waves which are propagated near the Earth's surface are called ground waves. So, whenever a wave, the electromagnetic waves are produced from the transmitting antenna, these electromagnetic waves will not reach to the receiving point instantaneously. So, they escape into the free space in different directions. They escape into the free space in different directions. So, as the distance increases between the transmitting antenna and the receiving antenna, the amplitude of the transmitted signal reduces. The amplitude of the signal mode, the amplitude from the transmitting antenna reduces. So as the distance is increased, there is some loss of energy when the signal reaches to the receiver. And moreover, when the signal is transmitted from the transmitting antenna, it spreads in different directions. And moreover, this transmitted signal will not reach to the receiver in only one path. It may travel in different paths. That means some waves will travel directly to the receiving antenna, and some rays will reflect from the ground and reach to the destination point, that is receiving antenna, and some waves will go to the topmost layer of the earth, and they are reflected back to the receiving antenna. So like this, the rays which are traveling from the transmitting antenna, they travel and reach to the destination point in different paths. So these different paths of propagation, we call it as modes of propagation. So these different paths of propagation, we call it as modes of propagation. All the waves traveling will not reach directly to the receiving point due to the reason that the earth is not flat. So we know that the earth is not flat, earth is curved surface. So moreover, as the distance increases, there is a more curved surface of the earth. So there will be some reflections happening from the ground towards the receiving antenna. So the waves which are propagated near the earth's surface are called ground waves. So the waves which are propagated near the surface of the earth are known as ground waves. So the ground wave propagation is possible when the transmitting and receiving antennas both are close to the earth's surface. So there are the three types of propagation we are having. One is the ground wave propagation, the other one is sky wave propagation, and the third one is space wave propagation. So in these three modes of propagation, we can transmit the signal either on the surface of the earth or from directly transmitting the signal to the satellite, and from the satellite to the receiving antenna. And we'll see all these modes of propagation one by one in detail later. So the ground wave propagation. So moreover, the ground wave propagation means the waves which travel over the surface of the earth. The waves which travel over the surface of the earth, we call it as a ground wave propagation. So the ground wave propagation is possible when the transmitting and the receiving antennas both are closer to the surface of the earth. So here you can see here the surface of the earth here. These both are closer to each other here. So, but as the distance increases, these waves cannot be traveled over the surface of the earth. Why? Because the surface is curved, more amount of reflections takes place. More amount of reflections takes place when the waves touch the ground. So when the distance between the transmitting and the receiving end is very less, then only the ground wave propagation is possible. Here, these ground waves can be classified as different types of waves. One is the space waves, the other one is the surface waves. The space waves is nothing but which travels directly from the transmitting antenna to the receiving antenna without striking the surface of the earth. We call it as a space wave. So without striking the surface of the ground, the waves which travel directly from the transmitting antenna to the receiving antenna, we call it as space waves. And surface waves are waves which strike the surface of the earth, which strike the surface of the earth, and reflection takes place, and these reflected waves will reach to the receiving antenna. So you can see here, this is the transmitting antenna, and this is the receiving antenna. This is T, and these are known as this is a space wave traveling directly from transmitting antenna to receiving antenna. And if we say the transmitting antenna and receiving antenna, if we take it clearly, this is the transmitting antenna and this is the receiving antenna. Some waves will touch the surface of the earth. These are reflected again to the receiving end. So such waves we call it as surface waves. Such waves we call it as surface waves or reflected waves or ground reflected waves. And here, the waves reaching the receiving antenna as a result of scattering and reflection by the ionization in the upper atmosphere is known as the sky waves. As you have seen there, the atmosphere is divided into three different types of zones. One is the tropospheric zone, and the ionospheric zone. So there are two different types of zones. We are having ionospheric layer and a tropospheric layer. So here the waves will travel either in the tropospheric layer or also ionospheric layer. So these layers are being defined with respect to the distance from the atmosphere, with respect to the distance from the surface of the Earth. That means the region of ionization in the atmosphere starts about 80 kilometers above the surface of the Earth. We call it as an ionospheric layer. So the region of ionization in the atmosphere above 80 kilometers above the surface of the Earth, we call it as ionospheric region. So here from 0 to 16 kilometers, from 0 to 16 kilometers, we call it as the region which is known as the tropospheric region, which we call it as the tropospheric region. So the waves will travel either in the tropospheric region or it may travel from above 16 kilometers also. So it depends upon the input signal we give. That is, it may be the very high frequency signal or ultra high frequency signal. So depending upon the input signal we give, this transmitter signal will travel in different paths between these layers only. So the waves that are going to reach, they are going to reflect and scatter in different directions between these layers. Hence we call it as the sky waves. As we are going to propagate the electromagnetic waves into the sky, hence those waves are known as the sky waves. So in the sky waves, there is a process which is known as ionization phenomena. That means the electromagnetic waves will collide with the ions in the layer, and the reflection takes place from the ionospheric region, and signal is going to reach back to the receiver. So due to the phenomenon of ionization, reflection and refraction takes place. Reflection and refraction is going to take place in the sky wave region. The sky waves resulting due to scattering in the ionosphere are also known as ionospherically scattered or ionospherically reflected waves. So both the reflection and also refraction takes place in the ionospheric region. So hence the sky waves resulting due to the scattering in the ionospheric are also known as ionospherically scattered or ionospherically reflected waves. The region in the atmosphere around 15 kilometers above the surface of the Earth is called as a troposphere. So the region in the atmosphere around 15 kilometers above the surface of the Earth is called as a tropospheric layer. So the waves which are reflected or scattered in the troposphere before reaching the receiving antenna are called as a tropospheric waves. So here you can see in the picture that the ground wave propagation, sky wave propagation, and the space wave propagation, different frequency ranges are used in all these types of propagation. So in ground wave propagation, the frequency range is limited only from 30 kHz to 3 MHz only. So above 3 MHz, we cannot transmit the signal by the ground wave propagation. And sky wave propagation, it is a 3 MHz to 30 MHz. That is, the signals can be propagated from the transmitting antenna. Only the operating frequency band ranges between 3 to 30 MHz. Similarly, the space wave propagation, we can transmit the signal only in the range of 30 to 300 MHz. We can transmit the signal only in the frequency range of 30 to 300 MHz. So the ground wave propagation, it is used for microwave radio broadcasting. The sky wave propagation, this method of propagation is used for point-to-point communication and also for long distance communication. So whenever we are going to transmit the signal around 50 kilometers or 100 kilometers, the better option we are having is the sky wave propagation and the space wave propagation. So we can transmit the signal for longer distances above 100 kilometers or 200 kilometers only by sky wave propagation or space wave propagation. Why? Because the loss of energy is very less in sky wave propagation and space wave propagation compared to the ground wave propagation. The space wave propagation is used for TV transmission and also the FM transmission. The FM signals and the TV transmission signals can be operated in the range of 30 to 300 MHz only in the space wave propagation. And what are the factors involved in the radio wave propagation? So these are the factors which will reduce the signal strength of the receiver at the receiving point. So whenever you're going to transmit the signal with a power of 20 watts, suppose this 20 watts of power is being radiated by the transmitting antenna. Moreover, the receiving antenna only we are getting 15 watts of power. That is, the 15 watts of power is absorbed by the receiving antenna. So here some amount of watts, that is the 5 watts of power is being wasted. There is a loss of energy of 5 watts between the transmitting antenna and the receiving antenna. So why there is a loss of energy of 5 watts between the transmitting and the receiving antenna? So there are some factors involved in the radio wave propagation which will reduce the signal strength of the from between the transmitting antenna and the receiving antenna. The first one is these are the characteristics such as conductivity, permittivity, and permeability. As we know that the earth is never rough or the earth is never smooth. That means at some point of view the earth is regarded as smooth, at some point of view the earth is regarded as smooth. So earth is smooth here, and at some regions the earth is rough. So when the earth is rough or smooth, generally the conductivity, the permittivity, and the permeability, all these three parameters will change. And hence the signal strength will be reduced. That means the conductivity of at one region is 1. The conductivity in another region may be around 1.5. Similarly, the permittivity epsilon and the permeability mu also vary with respect to the surface of the earth. So earth can be regarded as flat and earth is regarded as curved also. So both we are having two types of earth. At one surface we are having a flat earth, at one surface we are having curved earth. Hence the signal strength when the earth is curved, the signal touches the surface of the earth and this ground is going to absorb some amount of energy and the remaining amount of energy is being transferred to the receiving antenna. Hence due to the curvature of the earth also, the signal strength is going to reduce due to the roughness of the earth. And if we are going to transmit, when the earth is flat, the signal loss is very less. When the earth is flat, the signal loss between the transmitting antenna and receiving antenna is very less. But when the earth is curved, the signal loss is more due to multiple amount of reflections. Due to multiple amount of reflections from the ground, the loss of energy is more in a curved surface earth. And another factor which is involved in the loss of energy is the frequency of operation. So whenever we are going to select the frequency of operation, we need to select the mode of propagation. We cannot propagate above 3 MHz. Suppose if you want to propagate 5 MHz signal in ground wave propagation, it is not possible. So we can transmit to 5 MHz signal only either in the skywave propagation or in the space wave propagation. So then only the signal can be effectively reached to the receiver. So we cannot transmit above 3 MHz of signal. Above 3 MHz signal in the ground wave propagation. Why? Because the ground wave propagation is used only for the short range communication only. The height and the polarization of the transmitting antenna and the transmitting power are factors which influence on the reduction of signal strength. So the height of the transmitting antenna, that is moreover the transmitting antenna is placed on the base station. This is known as a tower. And on the tower we are going to place the transmitting antenna. And this tower, the base station, microwave station, is around a distance of it is 100 to 200 meters. At a height of 100 to 200 meters height, we are going to place the transmitting antenna so that the signal is directly propagated to the receiving antenna. When we place on the surface of the earth, some amount of energy is being absorbed by the ground. Hence, always the transmitting antenna is placed at a height of around 100 to 200 meters from the surface of the earth. And moreover, the vertical polarization is preferable rather than the horizontal polarization in case of a transmitting antenna. Why? Because if there is a vertical polarization, in the vertical polarization, suppose let us say the signal is going to the receiving antenna directly without any waves falling on the ground. Suppose if we place the antenna vertically, this is the vertical position of the antenna, then the antenna is said to be vertically polarized. Why? Because the electric field lines will travel directly to the receiving antenna like this without touching the ground. Suppose if the antenna is placed horizontal, that means it is said that the electric field is horizontally polarized. If we place the antenna perpendicular to the surface of the parallel, this is the surface of the earth. let us say the vertical polarization. So in vertical polarization, what is going to happen means the antenna is placed perpendicular to the surface of the earth. So when the antenna is placed perpendicular to the surface of the earth, no waves will touch the surface of the ground. But in horizontal polarization, when the antenna is placed parallel to the surface of the earth, this is the antenna, this is the antenna here. When the antenna is placed parallel to the surface of the earth, then all the waves will fall on the surface of the ground. Some amount of energy will be absorbed by the ground, and the remaining amount of energy is going to reach to the receiver. So whenever we're going to transmit the signal, we need to check whether the antenna is vertically polarized or horizontally polarized. So here the transmitting antenna is vertically polarized, then the receiving antenna must be vertically polarized. Then only all the amount of electric field lines will reach to the receiver, and the efficiency of the receiving antenna will be more, as because more amount of energy is being absorbed. Why? Because the receiving antenna is also vertically polarized. The distance between the transmitting antenna and receiving antenna is very important, because as the distance increases, we know that the amplitude of the signal, the transmitted signal will be reduced. So for long distance communication, we need to use the skywave propagation or space wave propagation. Why? Because we are going to transmit the signal at a distance of 50 kilometers. Suppose there is a transmitting antenna here, and the receiving antenna is here at a distance of 50 kilometers. So when the signal is traveling from the transmitting antenna to the receiving antenna, and when the earth is curved, multiple reflections are going to take place. So multiple reflections are going to take place. And we cannot use the ground wave propagation. So in that scenario, we are going to use the space wave propagation or the sky wave propagation. So we are going to transmit the signal into the space, into the atmosphere, and from the atmosphere, reflection, the reflected signal will reach to the receiving point. So this can be happen. This phenomenon can be happen only when the distance between the transmitting antenna and receiving antenna is very large, very large. So whenever the transmitting antenna and receiving antenna is very large, so we should propagate the signal to the very high frequency at a rate of very high frequency, and moreover we need to use the transmit the signal into the atmospheric region, that is the ionospheric region or the space wave region. And another parameter which will reflect the signal strength is the refractive index and the permittivity of the troposphere. And whenever we are going to transmit the signal from a rarer medium, from the rarer medium to the denser medium, the velocity of the electromagnetic wave signal will be reduced. The velocity of the electromagnetic wave signal will be reduced. And hence the refractive index mu will be varied. And hence the refractive signal mu will be varied. As the refractive index is varied, definitely there is an impact on the loss of a signal. There is an impact on the loss of signal. That means the signal slightly bends due to the refraction. As we know that when the wave is traveling through different layers of atmosphere, so there are different layers in the atmosphere, D layer, E layer and F layer. And if this is the transmitting antenna and if this is the receiving antenna, when the wave is going to penetrate from D layer to the E layer, here the one layer will be denser, the other layer will be rarer. So when the electromagnetic wave is going to travel from D layer to E layer or E layer to F layer or from the denser medium to rarer medium, refraction takes place. So due to refraction, the electromagnetic wave slightly bends and travels towards the receiving point, that is towards the surface of the earth. So here the refractive index and the permittivity of troposphere is also very important for long distance communication. So as the wave travels through different layers, the velocity of propagation of electromagnetic wave signal will be varied. As the velocity of the signal is varied, so definitely there is some loss of signal, or there will be some delay in reaching all the types of signals to the receiving point. So these are the general factors which involve in the radio wave propagation. So let us have a recap what we have seen in the today's session. So we have seen what is a ray, what is a ray friend, and what are the factors involved in the radio wave propagation, and what are known as TEM waves. The waves which are traveling from transmitting antenna and receiving antenna are traveling in the form of two types of lines are produced. One are electric lines and magnetic field lines. And these electric field lines and magnetic field lines are both are perpendicular to each other and also orthogonal to the direction of propagation of the wave. We call it as TEM waves. And what is a ray? A ray is simply a straight line which is traveling in one direction, that is in the direction of propagation of the wave. We call it as a ray. And a wavefront depends upon the surface of the earth. So if we a wave, there are different types of waves where I've seen that there is a classification of waves: the slow waves, forward wave, backward wave, uniform plane wave, and also non-uniform plane wave. So these are the different types of waves we have seen today, and also these are the different factors are involved in the radio wave propagation. That is the curvature of the permeability, the refractive index, the distance between the transmitting antenna and the receiving antenna, the polarization of the antenna, the roughness of the earth, the permeability of the antenna, the atmospheric conditions. All these are the general conditions which will show in the signal strength reduction between the transmitting antenna and the receiving antenna. So let us end the session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.